TLS is a communication protocol providing end-to-end secure channels with confidentiality, integrity, and pre-authentication. It's said that more than 60% of all internet connections based on HTTPS are using this protocol. And not different from many other protocols, it uses public key cryptography in some of the aspects, for example, in handshake and in signature algorithms. Version 1.3 of TLS operates basically in 4 different modes. The first mode is known as the certificate-based mode, where the authentication is only made by the server. The second mode is the PSK mode, or called the session resumption. In this mode, the TLS takes advantage of a previous connection and use the handshake of this first connection to make the process of the next connections being easier. The third method is called the mutual authentication, and this method is very similar to the certificate-based mode, but in this case, both the server and the client are authenticated. And the last method is called the post-handshake client authentication, which is similar to the previous one, but it happens with authentication from the server side, and after this handshake is finished, the server requests the client to authenticate itself. The quantum computer. The quantum computer is different from the classical computer in the very basic sense. A qubit, which is another name for a quantum bit, is not a dual state like a bit, like a classical bit. A qubit is represented by a linear combination of 2 states. So before the measurement of a qubit, it can be in a superposition of these 2 states. And this equation is, of course, normalized, and there is a chance of a qubit after measurement to be found on state 0, and there is a chance of this qubit to be found on state 1. And the sum of both of these chances of these probabilities has to be 100%. This figure is the representation of a qubit after some mathematical manipulation. This sphere is called the Bloch sphere. A quantum register is a collection of qubits, and it's mathematically represented by the tensor product of these qubits. There are 2 main models of quantum computation. The first one is the gate model that operates in a similar way as the classical computers. It is made over a circuit. This can also be called the circuit model, and this circuit is made by a number of gates, and a quantum register is initialized, and after the action of a certain number of gates, the circuit is finished and the computation reached to a result. The adiabatic model, it used the physics to produce a slow evolution in time of the initial state. This kind of computation is very suitable for minimization problems. Now I want to show some of the quantum algorithms that can be used to attack public key cryptography. The first one I want to mention is Shor's purified algorithm, made by Peter Shor in 1994. It provides an exponential speedup for solving factorization problems and discrete logarithm problems. Now there are some newer implementations of these algorithms that extend its usability for elliptic curves as well. There are some of the achievements with these algorithms shows that a good implementations use something around 2n plus 1 qubits in total, and roughly 3n to the power of 3 times log of n gates. So using this information, like if someone's trying to break the RSA, it's gonna need, like in this case, the RSA is using 2048 bits, and trying a Shor's implementation will require 4097 qubits and a huge number of gates. So creating a quantum computer with enough number of qubits and gates would allow us to theoretically break the RSA, but things are not this simple because there are errors in the measurement. And some of the ways to mitigate these errors, and I mean these error treatment is a science itself. It's not easy to do this, but some of the ways is by doing the calculations multiple times, or putting some of qubits that are noisy together to simulate one perfect logical qubit. And there are other things to consider, because each gates take a little time. There is a table on the screen showing different architectures for quantum computing and the time of its gates. Also, there is something called the coherence time, that it is the time that a qubit can remain with its quantum properties. So a computation cannot be longer than this coherence time. This is another problem. But other than the Shor's algorithm, there are some good adiabatic implementations that can solve the factoring problem and the discrete logarithm problem. This table below shows some of the achievements that both of these implementations, the Shor's algorithm and the adiabatic implementations, achieved across the years. threat model. Now we're going to start talking about the eras of the quantum computation. The pre-quantum era is the era we are now, where the quantum computers are not powerful enough to make an effective break on cryptography. And after this level of achievement, it starts the post-quantum era. It started by the post-quantum initial era, where the quantum hardware is still primitive and still expensive, demanding a high skill level to break even the short keys. And the coherence times are very short, the gate times are very long, and all the problems associated. Then I have the intermediate post-quantum era. That's just an era between the initial and the advanced era. And the advanced era is when the quantum computation is fully established and it's available at a lower cost. The quantum eras, we have the threat actors. The threat actors can be differentiated by the available resources they have, and this means the amount of money they have available for an attack, then and the number of personnel. These threat actors can also have a skill level, and with this skill level and the available resource they have, it's gonna tell when and at which stage of the quantum era they will become a threat. For example, organizations with a higher number of resources and also a very high number of skill level can become a threat in the very initial eras of the quantum computation. On the other hand, individuals will only become a threat with a high skill level and also in the advanced post-quantum era. The main capabilities of a quantum attacker on TLS are impersonation, which means pretending to be someone different, and breaking confidentiality, which means listening to confidential messages. Breaking confidentiality can be achieved by a passive attack, which is just listen to the communication channel, or by an active attack, which means actually changing the communication. Impersonation, on the other hand, can only be an active attack. Now, if the threat actor has a quantum computer and he can break the confidentiality of TLS 1.3 by first collecting the client-server hello messages, extracting the public keys inside, then using the Shor's algorithm for the elliptic curves to break the key exchange, and the last step, use the recover ephemeral key to derive the symmetrical key. On the second mode, which is the mutual authentication mode, the steps are the same. For the post-handshake mode, also the same steps. But for the PSK base, the resumption mode, it's a little bit different. You first use the same steps as used for the first mode. Then you use the recover ephemeral key to derive the symmetrical key used throughout the communication. Decrypt the new session ticket message, recovering the ticket information. Use this recover information to derive the resumption PSK, and then use the PSK to derive the second handshake symmetrical keys. Now, if the threat actor wants to impersonate, then on the first TLS mode, which is the certificate base, first, it collects the client server hello, extracting the public keys, then use the Shor's algorithm for the elliptic curves to break the key exchange. Third step, use one of the recover private keys to derive the symmetrical keys. And then decrypt the authentication messages. The fourth step. Then breaking the certificate messages. It can be used by two methods, which depends on the algorithm using for the signature. Here, it can be used the Shor's algorithm or an adiabatic algorithm to solve the factorization problem. If, for example, the signature was made with RSA, or it can use the Shor's algorithm for the elliptic curves to break the signature if a different DSA algorithm were used. On the second TLS mode, the multiple authentication mode, is the same steps for the server authentication if you want to impersonate the server, but in this case, the attacker can choose to impersonate the server or the client. In the third TLS mode, the post-handshake authentication, to impersonate the server is similar to the previous mode, but if the attacker wants to impersonate the client, it has to follow a little bit different steps. First, check the presence of post-handshake halt extension. Then, use steps 1 and 2 of the certificate-based authentication, which is the first TLS mode. 3. Decrypt the communication, use the recover symmetrical keys, searching for the certificate request message. And 4th, use one of the alternatives to attack the client certificate message and return the private key, which is using the Shor's algorithm or an adiabatic algorithm to solve the factorization problem if the signature algorithm is, for example, the RSA, or using Shor's algorithm for elliptic curves if a different algorithm for signature were used. On the PSK-based TLS mode, similar steps as used for server authentication mode are used, but the steps should be applied to the first handshake. Have the PSK information that attacker can impersonate both peers. However, PSK's duration time can be limited to up to 7 days, so the attack window is limited in this case. Here is a small research we did using the Wireshark. we use the Wireshark to capture packets of some of the most used websites during 1 hour. And on Instagram, we can see 1 hour of navigation on Instagram rendered 835 megabytes of information. On youtube.com, it was 723 megabytes of information. On amazon.com, it was 272 megabytes of information. On gmail.com, it was 124 megabytes of information. This number is, of course, approximate. It might change depending on the day and on user styles. But if the attacker wants to make a store now decrypts later attack and wants to storage 1 day, which is 24 hours of information, we can see that gigabytes of storage is necessary if the attacker wants to store 1 year of information. The amount of storage go beyond the terabyte. These, if one want to attack more users, this experiment is counting only 1 user. If you want to attack a group of users, you can multiply this by the number of users. Of course, the using style of each user will be different, but this number is as approximate value. Mitigation. First, there is quantum cryptography, which is the use of physics to create a different class of cryptography. This can be as simple as using the quantum superposition to create a perfectly random number. But the most common in this class of cryptography is the QKD. That's the quantum key distribution. The pros of using the QKD is the mathematics of quantum mechanics guarantee the key exchange is perfectly secure. The second pro is the no copy property of quantum mechanics ensures there will be no man-in-the-middle attack because a measurement of the system would modify it. The cons of the QKD. No copy property makes it impossible to reroute or broadcast a qubit, making it necessary special network channels and hardware. Second con, it is affected by the coherence, and most of the current QKD systems do not allow long travels. And the last, implementation costs. Implementation costs are very expensive for large networks, making it a viable solution only for limited use cases. The second type of mitigation is the PQC, which stands for post-quantum cryptography. This is the use of mathematical problems that are hard for a quantum computer to solve, running on classical devices. NIST in 2022 announced 4 algorithms promised to be quantum safe, which is the crystals Kyber, which is a quantum encapsulation mechanism that can be used to establish symmetric keys. The crystals dilithium, the Falcon algorithm. These two are DSA, which is the digital signature algorithms, and the Sphinx Plus, which is a hash-based digital signature algorithm. The pros of using PQC: they are more viable than for key exchange than use QKD. Second pro, there are also implementations for digital signatures. The quantum key distribution is just for key distribution, not for signatures. The cons of PQC: first, they have been tested for years, but it's still not possible to tell for how long they will remain unbreakable. Also, most of them are slower than traditional algorithms for the key exchange or for digital signature. It impacts on slower page loads and a risk of packet loss. There are also hybrid implementations, and these can be seen also as a subclass of the PQC because they combine a classical algorithm with a post-quantum algorithm to create a stronger cryptography that is secure against classical and quantum attacks. Some examples in this category is combining the output of a classical and a post-quantum algorithm with XOR operation in a key exchange. For digital signatures, creating two signatures, one with a classical and another with a post-quantum algorithm, are ways to mitigate the quantum threat. Other than these methods just presented, there are some others that are not a definitive solution, but they work on diminishing the return on investment and hopefully making the attack less interesting. These methods are creating a longer key because, as we've seen in some slides ago, a longer key requires more gates for quantum gates, and each gate has a time, so it'll increase the execution time for decryption, which can become impossible to finish an attack. Also, adding encryption layers with the intent to create to force the attacker to make consecutive attacks on each of these layers. So since the attacker has decrypted one of these layers, they don't have the access to the information yet. They have to decrypt all the other layers. Some protocols have implemented this PFS, PCS, key management, short-term certificates. All these are good ways also to diminish the data recovered on each attack. Or even in the short-term certificate specifically, can shorten the time window for an attack. And also, because the amount of storage necessary for starting another decrypt later attack is huge, companies have to be aware of social engineering attacks, because an attacker, since amount of storage is huge, the attacker may want to choose better which attacks he has to storage. So they might use social engineering to collect this information. Conclusion. On this presentation, we've seen the threats of quantum computing on TLS 1.3, existing quantum algorithms for an attack against the public key cryptography, achievements of these algorithms, detailed steps for a quantum attack in different handshake modes of TLS 1.3, approximate requirements for a star-now-decrypted attack, and mitigation methods. The references